What would you do if someone was chasing you wielding a piece of a microwave oven? Because that's exactly what happens when you are under attack by an active radar homing missile like the AMRAAM. Coming up. Welcome to Millennium 7 Star, the channel that helps you make sense of military history and military technology. Today we are talking about active radar homing, which is actually the homing technology of the principal air-to-air weapons in service with each country that has a serious air force. Mind, you won't find these things anywhere else on YouTube, so you may want to stick around till the end. But before doing that, please subscribe and hit the bell so you won't miss any episode. So, first things first, what is inside an active radar homing air-to-air missile? You have a propulsion section, usually a rocket engine, a control section, an armament section, and a guidance section, all encased in a cylindrical body with wings. And for those who wanted me to cut an air-to-air missiles with a chainsaw, well, sorry to disappoint you guys. So, missiles with active radar homing have a full-fledged radar in their nose. So, why would you put an active radar in the nose of a missile? Well, to give the missile a way to home on the target. The radar can tell the missile that at a specific distance, in a specific direction, there is a target which is also moving in a specific way. The guidance electronics manages the missile energy to get to the target by steering the aerodynamic surfaces or enacting any other form of control that is on board. I am sure you know the general principle of the radar. It is something that actually emits electromagnetic radiation into the sky. If the electromagnetic radiation gets to a target, it bounces back and there is an antenna that receives the signal. Some electronics measures how long it takes for the signal to come back, and since you know where you were looking, because the signal emitted by the radar is actually very narrow, very directional, you can actually show the position, the speed and the distance of the target like a nice little blip on a screen, which is obviously what a pilot sees when he's on board on the plane, but the missile doesn't use it. The missile obviously doesn't use the screen, but the signal about the distance and the position relative to the body of the missile is fed to the guidance electronics. Guidance electronics will use the aerodynamic surfaces on the missile or will use any other means of propulsion to steer the missile toward the target. Every guidance system has different components, either hardware and software. But for the moment being, let's focus on the information and the variables that actually are required to guide the missile toward the target. The input variables to the guidance system are first and obviously the target variables, that is distance, direction, speed and acceleration. The second set of variables are those related to the missile itself: speed, angle of attack, pitch, yaw and roll angles. The output variables of the guidance systems are the commands to the actuators that move the aerodynamic surfaces. The control system also generally has a feedback system that measures how effective was the command that was given and uses this input to actually calculate the following command. In general, the idea is to impart a lateral acceleration to the missile toward the target. In the scientific literature, this is sometimes called the latex. Please don't Google it. The algorithms implemented into the guidance system are normally a close-guarded secret, because if you understand the guidance laws and you know the dynamic performances of the missiles, well, you can also find the way to defeat the missile when it is launched. Try to ask a military pilot about the guidance laws of the weapons that he is using and you will see the kind of answer you will get. However, there is enough public domain material about those that we can safely say that the guidance laws fall into three main categories. In a pursuit algorithm, the guidance system tries to keep the velocity vector of the missile pointed at the target. I am saying the velocity vector and not the missile axis because missiles do fly with an angle of attack, so they may not be, in general they aren't the same thing. The logic behind it is simple. If you keep going toward the target, at some point you will get close enough for the proximity fuse to go off. Also, a pursuit law can point directly to the target or to a point slightly ahead of the target using the knowledge of the target velocity that can be acquired by the radar. This is quite an old law and a very simple one, and has the advantage of being simple, but it generally requires a lot of maneuvering when you get close to the target, so it uses a lot of energy in the final stage of the trajectory when energy is actually at premium. So it's not a particularly efficient one. Proportional navigation gets its name from sea navigation. Sailors know that from a ship, another ship appears to be stationary, but increasing in size, there is a risk of collision. The actual flight path has nothing to do with this, but it was this consideration that sparked the mathematics that it's used in the laws. The proportional name derives from the fact that the lateral acceleration that is imparted to the missile is proportional to the line of sight variation of the target, but also to a navigation constant. Pretty much is sort of a measure of how hard the missile is trying to turn. This type of navigation has been very successful till a few years ago because it is a good compromise. It is relatively easy to implement still, but also reduces the lateral acceleration, flying a more efficient trajectory than for example, a pursuit. Also, its mathematics lends itself to actually being tweaked and implemented with specific corrections that really augment and improve the guidance. One interesting aspect of proportional navigation is that the missile seems often to sort of anticipate the movement of the target, even though it really doesn't. The most modern weapons tend to use control laws that are based on optimal navigation. This is an entirely different concept. The idea of optimal navigation is trying to minimize the energy spent during the flight path. Obviously, in this case, you need to predict somehow the interception point, so a maneuvering target may be difficult to hit, but still these kind of laws are considered the most effective. What the laws try to do is to minimize the use of aerodynamic surfaces, because every time you steer the missile you bleed a lot of energy because the drag goes up, and also apparently bizarre choices like the lofting trajectory that we have mentioned in a previous video are actually rooted in the necessity of reducing the total amount of energy required to get from the launcher to the target. So far, this is what we know. It is relatively easy to find books or articles or paper that describe how to implement these kind of laws. I have to confess, the mathematics behind these laws is quite complex, and it is also a bit challenging, even for me, despite my master in aerospace engineering. However, implementing these laws requires a lot of clever know-how and an adequate circuitry. You have to consider that many of the weapons which are in service today have been designed maybe 20 or even 30 years ago. Despite the updates, the electronics that they have may not be as advanced as the electronics that we are used to. Actually, and this is a general point, weapons electronics may be generations behind the electronics available commercially to the general public. For this reason, the most sophisticated and computational heavy guidance laws could not be implemented in weapons till relatively recently. I mean, the first generation of air-to-air missiles wasn't even digital. Solid-state electronics started being used in the 70s before they still used valves. Thermionic valves, those glass things, those glass tubes that you see sometimes in hi-fi music amplifier. Yes, those things used in weapons, for real. Once the computational power of solid-state electronics and microprocessor became commonly available, it was possible to actually start implementing what I like to call tricks in the laws. That is, the performance of air-to-air missiles depends a lot on these small optimizations, small point additions that are made to the laws and can really make the difference between life and death. Obviously, these are covered under layers and layers of secrecy, so we can only conjecture what they are about. For example, an extrapolation could be that the most modern air-to-air weapons can predict the impact point based on a library of information about the target and its normal behavior rather than just its position and speed. But obviously, we don't really know. When a fighter pilot detects a target and is cleared to attack, what he wants to do is put himself in the correct position to use its weapons. In principle, every air-to-air missile has a no-escape zone which moves to the launcher and it is close to it. The size and the shape of this zone actually depend from the launcher, on the missile itself, and the characteristics of the target. A pilot in general may want to launch a missile when the target is within this no-escape zone, but it's obviously not always possible. Often shooting at long range but with a low probability of hit is useful to keep the opponent defensive. On the flip side, the pilot needs to consider that there is a limited supply of air-to-air missiles. If you are thinking that it is very complicated, well, yes it is, and to be honest, there's nothing really simple in this video. Normally a pilot detects the target by the onboard radar. The aircraft radar is normally more powerful and more sensitive than the missile radar. Antennas are larger, power supplies are, well, more powerful, and there is more room for more sophisticated signal processing. Missile radars need to pack everything within the missile nose, so it is just intuitive that they will be able to detect the target at shorter distances. It is just a matter of geometry. Their seeker emits less electromagnetic energy. That's it. This means that missiles that are actually capable of flying longer than their radar range need to be guided in the initial phase of flight. This mode of firing an air-to-air missile is called lock-on after launch. So it works like this. The pilot identifies and tracks the target with its own radar. The onboard computer calculates a firing solution that is a set of instructions to be given to the missile. The missile is fired and starts its flight according to those instructions, also using some form of inertial guidance, and for the most modern weapons, GPS or satellite positioning systems. The firing plane keeps tracking the target and eventually updates the missile, causing it to alter its trajectory if it is necessary, and it leads the missile to the point where the missile can turn on its own radar and acquire the target. This stage of the missile flight, when the onboard radar is switched on, is called going pitbull. After the missile has acquired the target, then the missile will try to hit the target on its own, and the launcher is free to evade and do anything else. Eventually, a boom follows. This principle that I have just explained is called mid-course guidance, and in itself opens an entirely new can of worms. There are several different types of guidance laws to optimize the missile flight during this mid-course stage, and they are as important as the laws that we have discussed before. And even more so because it is advantageous for the missile to turn on its own radar as late as possible, not to warn in advance the target. There are several different technology solutions to communicate with the missile. It could be the aircraft radar communicating with the missile. It could be a radio data link. And the data link itself can be one way, that is the aircraft telling the missile what to do, or two ways, with the missile talking back to the plane, informing the plane about its own conditions, or potentially even acting as a remote sensor. The launcher radar is not the only sensor that can be used to produce the information required to guide the missile. Modern planes all have an infrared search and track system, that is a passive system based on the infrared emissions of the target. The Russians pioneered the infrared search and track in the 70s. The infrared search and track is particularly effective because in this way the system remains totally passive and no radiation is emitted, so the launcher is more difficult to be detected and the missile as well. Another aspect to consider is that network-centric warfare is becoming increasingly more common, especially in the Western world. So the mid-course guidance information can be provided to the missile by platforms different from the launcher. It can be a different plane, it can be the OWASP, it can be a ground interceptor, it can be something else. Obviously, nothing of the above happens if the missile can acquire the target before being launched. This operation mode is called lock-on before launch. LOBO. If lock-on after launch allows for longer ranging, lock-on before launch has a shorter range but also relieves the launching plane from the burden of actually guiding the missile. So the launcher can evade eventually other shots or can do whatever is considered appropriate at that moment in time. And often it's considered appropriate to, for example, evade a return shot. Yes, I believe it is appropriate. You actually may want to think that the longer the range, the better, but often in the real world it is not always like this. For example, in the real world you may have rules of engagement that require that the target is actually identified visually. In this case, any range advantage is pretty much gone. Or, if you can use a long-range engagement, you still have to consider that at long range the kill probability, the probability of success, is definitely lower than a shorter range. And since every plane can carry a limited number of air-to-air missiles, which are generally scarce weapon, very expensive, so you don't want to waste them, you may want to use them in a situation where the probability of kill is better. And this almost always means closing the distance. So, which are the pros and the cons of active radar homing? Well, a very big pro is that it is a very accurate guidance system. It can bring the missile very, very close to the target, so the effectiveness of the warhead can be multiplied just by exploding very close to the target. The other big pro is that the active radar homing can be used at long ranges with a lock-on after launch or at short ranges with lock-on before launch. You have one weapon for long-range engagements and short-range engagement as well. The fire and forget capacity that comes with active radar homing is also obviously a big plus. The big con is the fact that the sensor is large, bulky, complex and expensive. This means that you can put one only in relatively large missiles, which actually means that you are by definition drawn toward medium and long range weapons. Also, cost and complexity means that the number of weapons available is limited, and in case of a long conflict they probably can't be manufactured quickly enough. Okay, we have just scratched the surface about active radar homing. Please let me know in the comments below what you want to know about active radar homing, what you want to know about missile guidance systems. If you like this video and if you want to support me, well, there are some recommended readings below with some affiliate links, but even just subscribing and hitting the bell is definitely enough for me, and it means the world. And if you want to learn more, please have a look at the videos beside me. For the moment being, thank you very much for watching. Goodbye.